A device called an altimeter measures altitude or the height of a point above sea level. Pilots of aircraft and spacecraft use altimeter to keep track of their height above the Earth's surface. The altimeter is one of the most important instruments in the airplane because it is the only one that provides altitude information. Altimeters are also used by mountaineers and skydivers to determine where they are on the ground or in the air. Barometric altimeters are the most popular kind. By measuring air pressure, they can determine altitude. Air pressure drops as altitude rises. This is due to the Earth's lower density at high altitudes. Less force is applied to the Earth below. The readings on an altimeter fluctuate as elevation changes. Understanding the altimeter's operation and how temperature and atmospheric pressure affect it is essential for effective use. Weather can also affect altitude readings because the air pressure drops during storms. An altimeter can be worn on the wrist or mounted on the instrument panel of an aircraft. A stack of evacuated corrugated bronze aneroid capsules serves as the sensitive component in a sensitive altimeter. These aneroids are subject to air pressure, which strives to compress them while their inherent springiness strives to expand them. As a result, the air pressure changes, and so does their thickness. As the pressure varies throughout the instrument's usable range, stacking several aneroid objects increases the dimension change. Principle of operation. The aneroid altimeter is calibrated to show the pressure directly as an altitude above mean sea level. In accordance with a mathematical model atmosphere defined by the International Standard Atmosphere or ISA, older aircraft used a simple aneroid barometer where the needle made less than 1 revolution around the face from 0 to full scale. This design evolved to 3-pointer altimeters with a primary needle and 1 or more secondary needles that show the number of revolutions, similar to a clock face. In other words, each needle points to a different digit of the current altitude measurement. However, this design has fallen out of favor due to the risk of misreading in stressful situations. The design evolved further to drum-type altimeters, the final step in analog instrumentation, where each revolution of a single needle accounted for 1,000 feet 300 meters, with 1,000-foot increments recorded on a numerical odometer-type drum. To determine altitude, a pilot had first to read the drum to determine the thousands of feet, then look at the needle for the hundreds of feet. Modern analog altimeters in transport aircraft are typically drum-type. The latest development in clarity is an electronic flight instrument system with integrated digital altimeter displays. This technology has trickled down from airliners and military planes until it's now standard in many general aviation aircraft. A sensitive altimeter has a barometric scale that can be adjusted, allowing the pilot to choose the reference pressure from which to calculate altitude. A tiny window known as the Guzman window allows you to see this scale. The scale on the instrument is changed using a knob. The scale's range is 948 millibars to 1050 millibars, or 28 in mercury to 31 in mercury. In aviation terminology, the regional or local air pressure at mean sea level is called the QNH or altimeter setting, and the pressure that will be calibrated the altimeter to show the height above ground at a given airfield is called the QFE of the field. An altimeter cannot, however, be adjusted for variations in air temperature. Differences in temperature from the ISA model will accordingly cause errors in the indicated altitude. Air pressure isn't a requirement for all altimeters. By triangulating signals from various satellites, the Global Positioning System or GPS, for instance, can provide altitude as part of the location of an area. Radar and laser altimeters found on some aircraft and spacecraft work similarly to sonar measurements of the seafloor. These altimeters send a radio or laser signal toward the surface and measure the time it takes for the signal to bounce back to the aircraft is then translated to an elevation. Accurate topographic maps of both land and ocean surfaces can be produced by combining altitude measurements from radar and laser altimeters when they are used in satellites. 95% of the ocean surface topography was measured by the radar altimeter on the Topex or Poseidon satellite, for instance. The radar altimeter on Topex or Poseidon was developed by NASA, the US Space Agency, and CNES, the French Space Agency, and was accurate to within 2 centimeters. Together with another satellite, the Jason-1, Topex or Poseidon plotted the rise in the world sea levels, establishing a link between the two phenomena. The scientific principles behind the altimeter were first written by Rev. Alexander Bryce, a Scottish minister and astronomer in 1772, who realized that the principles of a barometer could be adjusted to measure height. Precision of an altimeter is crucial for accurate and efficient pressure measurements. Without precise measurement of pressure, altitude can't be measured properly during flight, which could result in hazardous safety risk and extreme damage to an aircraft.